Hello everyone, welcome to Numerical Methods class. In this video, we will talk about Chapter 3, which is about approximations and round-off errors. First of all, let's start with the definition of error. Error is actually a discrepancy, and in the numerical solutions, because they are just an approximation, we will have a difference between the exact solution and the numerical solution. And that's why there will be a discrepancy between this exact solution and the numerical solution, and we call this as error of numerical solution. So if the exact solution is available, we can easily calculate the error of the numerical solution because we simply just subtract them. However, for many problems, there is no exact solution available to calculate the error. Usually we use the numerical methods when we don't have the exact solution or when we don't have the analytical method. That's why we use the numerical methods actually. In that scenario, we don't have the error or the exact solution. And in these cases, we must settle for approximations or estimates of errors. And there will always be errors in numerical predictions. And the question here is how much error is present in our calculations and is it tolerable? So we will talk about these issues in this chapter. There are two types of errors for the numerical methods. The first one is the round-off error, and the second one is truncation error. And the round-off error, we will be seeing this round-off error information in Chapter 3. And for the truncation error, we will talk about it in Chapter 4. So first, let's start with round-off error. And it is actually the discrepancy introduced because computers can represent only quantities with a finite number of digits. That means that if we chop off some numbers from the some digits from the number, we will have a round-off error. And the truncation error, on the other hand, is the discrepancy again introduced by the fact that numerical methods may employ approximations to represent an exact mathematical operations or quantities. In other words, because we use some approximations of analytical approach using the numerical method, this will create a difference, and this difference gives the error actually. And this error is called truncation error. In other words, round-off error is because we cut some digits from the number. That's why we have some error. And the truncation error is because we are using numerical methods with some approximations instead of using an analytical or exact solution, and that gives an error. In addition to these, we will have some other errors which are not directly connected to the numerical methods. Those are called blunders, formulation or model errors, and the data uncertainty. So we will talk about these in Chapter 4 as well. In this Chapter 3, we said that we will talk about round-off error, but before talking about it, let's define significant figures because this will be important for us. Significant figures or digits of a number are those that can be used with confidence to represent a number. So here you can see an example of speedometer and odometer. This is basically the speedometer and this is the odometer. In the speedometer, you will see that we have a speed value shown by this arm. And if we zoom in, we see that it is 45, 6, 7, 8, 9, 49 actually. And we also mentioned it here. But this 49, maybe we can say that it is 48.8 or 48.9. This is not clear, but because it's a little bit lower than 49, we can say this value. So the 49 is the value that we see confidently. We can easily say 49, but we can also say 48.9. So this kind of confidence gives us the number of the digits that we show to represent this speed value, for example. And these numbers or digits are the significant figures that we can write down about this speed. And basically, the significant figures include what we see confidently. For example, another number here is in the odometer, and you can see that it is 87,000 324 kilometers this car actually traveled so far, and also there is about like between 4 and 0.4 and 0.5 there is a value as well. And this, we can read this odometer up to 1 2 3 4 5 6 digits. So that's why we can say that we are confident up to 6 digits, and we can say that we have 6 significant figures for this odometer value. Or maybe we can say that between 4 and 5, we can just say maybe 45 here, and we can increase this to 7 maybe. So this kind of number of digits that we can write a number is called the significant figures. And this will be important especially for the round of error, because in the round of error we will show a number with a certain number of digits, which are called the significant figures actually. So let's talk about some notes on significant figures, especially the use of zeros in the figures, in the numbers. So the zeros are not always significant figures because they may be necessary just to locate a decimal point. Here there is an example. You can see 3 numbers, and these all 3 actually have 4 significant figures because the zeros before the numbers are not considered as significant digits. Here, starting from 1 to 5, these are the significant figures. Here it is the same, here the same. Although the numbers are different in magnitude, the number of significant figures that represent these are the same. So these zeros are preceding the numbers, but these zeros can be after the numbers as well, so we call them trailing zeros. So in a similar way, if we have trailing zeros in large numbers, it may not be clear how many of these are significant. So we can simply add some zeros after this. For example, here there's an example, 45,300. So we have 2 zeros over here. But we need to be sure if these are necessary to show or not. If we don't sure about the confidence of these zeros, we can simply show it by 4.53, and this has just 3 significant figures, and it is still 45,300 by adding this 10 to the power 4. But if we are sure that there is 1 zero for sure over there, then it is shown by this, and it has 4 significant figures, and we are confident that there are 2 zeros, then we can show like this, and this is 5 significant figures. So instead of showing like this, to highlight the significant figures that we can use, we can simply use this scientific demonstration or expression, which shows the number with the 10 to the power the value. Let's talk about some implications of significant figures. First of all, because the numerical methods give approximate results, we must develop a criteria to specify how confident we are in our approximate result. And we use significant figures for this purpose. For example, for the parachutist example, the analytical results at 10 seconds, we already calculated this in chapter 1, that V is 44.92 meter per second. And you can see that this gives 4 significant digits. So that's why then we can conclude that we are expecting to have with confidence 4 digits in the numerical result as well. So then in the numerical result we can use, because in the analytical result we use 4 digits, in the numerical as well we can use 4 digits. Although we may find more digits in the numerical result, because we know the exact solution, it's better to use the same number of digits in the numerical result as well. And here also we show at 10 seconds. This was the approximation, if you remember. But if you don't know the analytical result, then whatever value the numerical result gives, we can use that as a significant digits. Secondly, the quantities such as pi, exponential, or root square 7 represents some specific quantities which doesn't have a limited number of digits. So these actually have an infinite number of digits. For the pi example, you can see that it goes from 3.14 up to infinity. So we need to chop this off at some point. And the cutting off point is actually based on the power of the computer, because the computers only represent a finite number of significant figures. And that's why, for example, for this, maybe this can be shown in a computer, but in a calculator, it's a computer as well. Maybe we can only see the first 7 or 8 figures. So the omission of the remaining significant figures is called round-off error. Basically, because we just omit some numbers in computers, we have a round-off error for the exact value. So this kind of implications are important, and we also define the round-off error here. And the concept of significant figures defined here will also have relevance to our definition of accuracy and precision, and we will talk about the accuracy and precision in the next slides. In this slide, we will talk about the accuracy and precision terms. Let's start with the definition of accuracy. Accuracy is actually refers to how closely a computed or measured value agrees with the true value. So it's basically the difference from the true value, let's say. And at the bottom, you can see an example. In here, the bullet holes, I mean the black holes over here, you can see that those show the predictions. And the bullseye, or the center of these circles, is the exact value, or the true value. So, and you can see that in each there are some differences from the true value. And if we want an accurate prediction, we need to be able to capture this center value. So here, for example, this black dot here, the prediction is very close. Here also very close. These are very accurate, but the remaining are not accurate. Over here as well. So you see that in D especially, we have for all the samples or all the predictions, let's say, we have very good accuracies. But in here, the accuracy is not good. Here, only a few of them, only one of them is accurate. Here, it also seems to be accurate around the center, but still there is a scatter which reduces the accuracy. So this scatter of the accuracy is called precision, and simply it refers to how closely individual computed or measured values agree with each other. So here, for example, they are scattered in a narrow range. That means it's very precise. Here as well, these are precise. They are very close to each other, because precision is between the measured values, or between the predictions, the closeness between the predictions. But these are away from the true value. So these are inaccurate, or accuracy is low, but the precision is high. And you can see this graph is already showing that actually. Increasing precision in the y-axis towards the bottom, and increasing accuracy to the right. So we can see simply that this is accurate, but precision is not good. This is both accurate and precision is also good. This is not accurate, also not precise. And this is precise but not accurate because it's away from the truth. And the opposites of accuracy and precision are inaccuracy and imprecision. Inaccuracy is also called bias. And you can see, especially in the figure C, that these are away from the center. Although they are very precise, very close to each other, they are away from the center. That means they have a bias or inaccuracy. For the precision, and so we can compare also this with this, and we can see that this is precise. This is also away from the truth, but also this is these predictions are away from each other too. That means these are not precise, or there is an imprecision. Imprecision, also called uncertainty, meaning that there is a large scatter of the data. So the data is away from each other. So if the distance between the data increases, the uncertainty or imprecision increases as well. And we don't want this. We actually want a precise as well as accurate prediction, this one. So D is optimal for us. But of course, with the numerical methods, we are not, although we want this, we will not be able to get always this kind of predictions. But still, we want an accurate or unbiased prediction and precise enough for adequate engineering design. So we will use the collective term error for the differences, including inaccuracy and imprecision. So these two combined together to define the collective term error. And with these concepts as background, with the accuracy and precision, we can now discuss the factors that contribute to the error of numerical computations.